right, so welcome to Math 355, lecture 14. This is the hottest lecture of the semester. Not because of the content, but because we've just had a 2-week spring break, and it is always hard to come back after being gone for a while. So I deliberately have structured the semester accordingly so that we are going to be reviewing a bit of what we've already seen and talking about how should we think about new concepts, new quantities. So I think Silverman does an excellent job in the book of going through and talking about how can we get to finding the right quantities to study. Most of you, yes. Oh, sure, I thought you were, okay. Most of us are not going to become professional mathematicians, and if we are, most of us are probably not going to be working in group theory. So in terms of the content, you may not be using the content that much, but the idea of how do you attack something new, how do you figure out what's good, what's worth studying, that's something that can stay with you, for the rest of your life. And that's why I really want to go slowly today, emphasize how do we think about things, and then you ease back into the semester. If people want to see more details, there's far too much to do. We can then do the flipping classes on Thursday, where one class will do theory, one class will do more problems, and then continue that on Tuesday. So if you want to see more things done than I can do here, just let me know. Okay, so the first is, as always, G will be a group, as always, H will be a subgroup, and then we denote the set of left cosets of G by G mod H. So whenever you see a definition, you should always have an example in your mind. So what's our go-to example for a group and cosets? Clock groups, excellent. So we can have G is equal to the integers. We can have H maybe equal to n times Z for some integer n, and then we get the clock group. And these would be things of the form, A plus NZ, where A can go from 0, 1, 2, all the way up to n minus 1. So there's more than one way to write a coset. Another way to write a coset 5 plus 12Z. How else can I write the coset 5 plus 12Z? So what's another way of writing 5 plus 12Z? So I'm taking 12Z. So I'm taking all the integers that have multiples of 12, and I'm adding 5, and that gives me a set. What's another way of writing this exact same set? 17. And again, no one is going to say anything other than 17. 17 is the most natural. But instead of 17, what else could you use? So you're saying 7 plus 12Z is the same as minus 7. Yes, minus 7 plus 12Z. So there's actually infinitely many different ways of writing the same coset. And we want to be careful that it would be terrible if when we do calculations, it matters which way we write something. So if I give you A plus NZ, I give you B plus NZ, how should we define the sum of A plus NZ and B plus NZ? A plus B plus NZ, or it's the same as A plus B mod N plus NZ. These would all be the same. And then the question is, are the cosets a group? So what do we have to do to show that the cosets form a group? What properties do we have to show? Close, and this is why I'm doing this very good review. So close. So if we have A plus NZ plus B plus NZ with A plus B plus NZ, yes. What else do we need? Associativity. Why do we have associativity? Inheritance, right? It's a great word. What else do we need? Identity. What's the identity? What would be the identity element for coset addition? I'm sorry? NZ is 0 plus NZ. We have to write it as something plus NZ. And what's the last one? Inverse. And so if I give you A plus NZ, what would be its inverse? You could do minus A. I think there's a better way of writing minus A. I would rather write it as N minus A. And then that way I could say, I can take all of my coset representatives to be from 0 to N minus 1. And so here, it turns out that it is a group. And then the question is it always a group? And the answer is yes, if G is, does anybody want to guess on a property on G that will make everything work out well? Your dream property for a group. So a group has to be closed, has to be associative, it has to have an identity, it has to have inverses. But if you're lucky, the group has an additional property. Commutative. So it turns out if G is commutative, then the set of cosets will always be a group. Unfortunately, there will be times when the set of cosets is not a group. Why do we care about this? If you think back to your chemistry days, you try to understand a complicated compound by breaking it up into simple ones, into the atoms. If you think about number theory, we try to break numbers up into primes. I want to try to break a group up into a subgroup H and its cosets. Because, really formally you should be thinking G mod H times H, the H's cancel and I get back G, right? This is, a legal thing, but that's what I'm really trying to do. I'm trying to take a complicated group G, take a smaller subgroup H, which I can understand, and then look at G mod H, which should also be smaller than G. So I don't want trivial. I don't want H to be G, I don't want H to be the identity, because then I'm not really breaking things up. I want G mod H and H to both be strictly smaller than G and strictly larger than the identity. And the goal is, if we can do this, the hope is we can understand G by understanding two simpler objects. And then what would you do with each of those simpler objects? So I now have two simpler objects, H and G mod H. What would I do to those groups? So I'm trying to understand G, and I try to break G up into two simpler objects. And then what would I do to those simpler objects? Yeah, try to break them up into simpler objects themselves. And you keep doing this as far as you can. How much can I keep breaking things down? So unfortunately, it's not always going to be the case that coset multiplication is well defined. So here is a simple algorithm. Let's take two cosets, C1 and C2 of H. And we're going to choose some element G1 in the first. We'll choose some element G2 in the second. And then we'll define the coset to be G1 times G2 times H. Now, when we looked at cosets for the clock group, this was perfectly fine. If I chose 5 or 17, it wouldn't matter, because when I did my coset arithmetic, 5 and 17 acted the same. It would be wonderful if that was always the case. And so the worry is, say G1, G1 prime are both in C1, and G2, G2 prime are both in C2. Is G1, G2H equal to G1 prime, G2 prime H? If that's the case, then we're fine. And then we can take any coset representative for C1 and any coset representative for C2, and the multiplication is well defined. But if it depends which representative I take, then that's not so good. So let's try to explore what this would mean if we want them to be the same. So to be the same, so we need G1, G2. Let's write slowly. So there has to exist an H1 in H such that G1 equals G1 prime H1. Why is that the case? What identity? Well, this is because G1H is equal to G1 prime of H. So what does it mean for two cosets to be the same? They have to differ by some element in H. You could multiply. This is the same as, H equals, say, G1 inverse G1 prime of H. So G1 inverse G1 prime has to be something in H. And so I've got things the wrong way. So I've got, G1 prime is equal to G1H like this. So then G1 prime H inverse is G1. So if I want to have two cosets to be the same, then they have to differ by multiplication on the right by something in H. Because anything in H times big H is just big H again. So if I tell you that G1 and G1 prime are both in the same coset, then they have to differ on the left by some multiple of H. Oops, this is supposed to be subscripts, not superscripts. Similarly, there has to be an H2 in H such that G2 is G2 prime H2. So we want G1, G2H to equal G1 prime, G2 prime, big H. So what do we need to be true? We need G1, G2 to equal what? So if I want, here. Well, what do we know about G1? G1 is equal to G1 prime H1. So this is the same as G1 prime H1, G2 prime H2 equals G1 prime, G2 prime H. Because I have G1 is just G1 prime H1 and so on. So if I want these two products to be the same, what must be true? So what's the only way that these two cosets can be the same? I want G1 prime H1, G2 prime H2 big H equals G1 prime, G2 prime H. What must be true if these two cosets are the same? Well, we don't have H1 and H2 next to each other. When are two cosets the same? We just did this a moment ago. When are two cosets the same? Good, and where is that multiplication happening? Somewhere on the right. So we need an H in H such that G1 prime, G2 prime equals G1 prime, H1, G2 prime, H2, H. That's what we would need for these two cosets to be the same. Now, If the group was commutative, we'd be fine. Because if G was commutative, we could then move the H1 through the G2 prime, and then we would just choose H to be H2 inverse, H1 inverse. So if the group is commutative, then we're okay. If H is the center, we're okay. The center is the set of all elements that commute with everything in G. So we're okay if H is the center of G. Or actually, it doesn't even have to be the center, it just has to be a subset of the center of G. But in general, I can't just push the H1 past the G2 prime. Do these two expressions look a little bit alike? What do they have that's good? What makes them look similar? Right. So do they both start off like that? Okay, so they both start off with G1 prime. So we can write this as G1 prime, G2 prime is G1 prime, and then we've got H1, G2 prime, H2H. And wouldn't it be wonderful to have a G2 prime here? I'm sorry? It would be amazing. But we can't just put a G2 prime there. But what could we put? So I can't just shove. Right, because we don't have nearly enough subscripts and superscripts and whatnot. So if we put in a G2 prime, G2 prime inverse, that's just the identity. Now, this is an H. Right? And so if in H we win. So all works if for all G in G, for all H in H, G inverse HG is in H. So we've come up with a very natural condition. If this holds, then this product is well defined. And then you could ask, is this the minimal condition that will work to have the coset, the set of cosets, giving us a group? This will work because if we know that G inverse HG is an H for every choice of H and H and every choice of G and G, then yes, this will be G1 prime, G2 prime times something in H. So all we have to do is find subgroups that have this property. Okay? Does everybody understand the calculation? We're trying to show when does coset multiplication not depend on which representatives we choose. Unfortunately, it might depend on which representatives. And so the hope is that we can find a natural condition so that it doesn't depend. And so I'm not going to go through all the details. I'll just start. The rest of the calculation is in the book. Again, if you want to see me do it on Thursday, let me know. This is an example where for one of the subgroups, the set of cosets will not be a group. So this is one of the best examples, one of the simplest examples of a non-commutative group. So this is back from chapter 2. We're looking at symmetries of an equilateral triangle. So we label the three vertices 1, 2, and 3, and we look at the different group elements. And so what we're going to do is we're going to write them down in explicit form and do the calculations. So the first one is the identity. And the way we're going to write this down is, this really nice notation. We're going to write, 1, 2, 3, and then below we're going to write what everything goes to. So for the identity, what does 1 go to? 1, yeah. So 1 goes to 1, 2 goes to 2, and 3 goes to 3. The next one is it's a rotation. So we move 1 to the 2 spot, 2 to the 3 spot, 3 to the 1 spot. So if we look at this, we want to write down what does this rotation do? It sends 1 to 2, it sends 2 to 3, it sends 3 to 1. The next rotation is going in the opposite direction. It sends 1 to 3, it sends 3 to 2, and so on. And so it would be 1, 2, 3. 1 goes to 3. Yes. And where does 2 go to? 1. Do I have to try to figure out what 3 goes to? Why not? But there can't be any repetitions. So the only possibility for 3 is whatever I haven't used yet, because it's the last one. So I know 3 has to go to 2. I don't have to do the calculation. For the next one, I'm flipping about a line from 1 to the side opposite it. So 1 stays the same, and then 2 and 3 just switch. For the next one, I'm flipping about 3. So 3 is going to stay the same. And now 1 and 2 flip. And then for the last one, 2 stays the same, and 1 and 3 flip. Okay. So let's do some calculations. So let's take 1, 2, 3, 2, 3, 1. So this is R1. I'm going to do the calculation twice. And let's take one of the flips. Let's take the flip 1, 2, 3, 2, 1, 3. So that is F2. So 1, 2, 3, 2, 1, 3, F2. And let's see what we get. So let's see if order matters. So for the first one, I do R1 first. So 1 goes to 2. Then I do F2, 2 goes to 1. So where does 1 end up going to? So 1 goes to 2, 2 goes to 1, so 1 goes to itself. For the bottom one, 1 goes to 2, 2 goes to 3. So where does 1 go? 1 goes to 3. That's already enough to show that the group is not commutative. That's already enough to show that the order of multiplication matters. Let's go back to the first one. 2 goes to 3, 3 goes to 3. So 2 just goes to 3, and then 3 has to go to 1. So what element is that? Well, I look down below and I see, oops, sorry. I wrote the wrong thing. 3 goes to 2. So that has to just be the element F1. And for the bottom one, 2 goes to 1, 1 goes to 2, so 2 stays the same. So then 3 has to go to 1, and then that has to be F3. So this is an example of a non-commutative group. Okay. I need to have a non-commutative group because we know if we have a commutative group, then coset multiplication is always going to be well-defined. It's not going to matter which representatives I use. So the only chance I have of something breaking down is to choose a group that's not commutative. This is the simplest example of a non-commutative group that I can really think of. And now, if you look at the book, read book, and you'll have an example where coset multiplication is defined, and one where it's not defined for subgroups here. So one of the subgroups is actually going to lead to everything working. One of the subgroups is going to lead to things fail. So you want to just roll up your sleeves and you want to just do some of these calculations. So I strongly urge you to read the book, go through the calculation. If you want me to do the calculation in class on Thursday, happy to do so. So this just shows us, unfortunately, that it is not always the case that I can take a subgroup and look at the set of cosets and have the set of cosets a group. And again, I want to do this because I'm trying to understand a complicated group by trying to understand simpler ones. Okay, so For all cosets, C1 and C2, for all pairs of elements, G1, G1 prime, and for all pairs of elements, G2, G2 prime, we want this to be true. So this is a great condition. If this is true, then coset multiplication is well defined. So if true, coset multiplication is well defined. Can somebody give me a subgroup of G where you know it will be normal? Where everything will be well defined? Whenever I ask this question, there should be 2 or 3 things that quickly go into your mind. So can you give me a subgroup of G where G1, G2H will always be G1 prime, G2 prime of H? And what should be your go-to things to check for subgroups? The identity and the whole thing. So if I take H to be G, then clearly it's true. If I take H to be just the identity element, it's true. So it's trivially true if H is just the identity for all of G. My next question is, does there exist a G with no non-trivial subgroups? So can you give me a G that has no non-trivial subgroups? So, yeah, but then, so you could do the identity. I want something other than just the identity. So do we have any theorems that tell us about the sizes of subgroups? I'm sorry? Okay, so let's consider, G equals the identity, little g squared, little g cubed. How high should we go? Can I go to any power, or is there only certain powers I should stop at? I'm sorry? To what? To prime power? Not quite, almost. Because if I stop at 7, I would have 8 elements. It's 1 less than a prime. I go up to G to the P minus 1. By Lagrange, no subgroups. Right? If I took instead G equals, say, E, G, G squared, all the way up to G11, then I could have, E, G squared, G to the 4th, G to the 6th, G to the 8th, G to the 10th. I could have E, G cubed, G to the 6th, G to the 9th. I could have E, G to the 4th, G to the 8th. I could have E, G to the 6th. I could have lots of subgroups in that case. But if I choose my group to have prime order, then it has no subgroups. If it has no subgroups, it has no chance of having a normal subgroup. So in some sense, this would be an indecomposable. I can't break something like this down further. And then the question is, well, what if my group has order prime squared? What would that structure look like? And that's something we'll actually answer before we finish this chapter. What does a group whose order is p squared look like? And then the more factors you have in the order of your group, the worse and the more complicated things are. If the group is abelian, it turns out we understand everything very easily. If it's not abelian, we understand it, but it's a tremendous amount of money. Fields medals were won for the analysis there. So this is just, it's always good to just have some examples in mind. Here's a group that has no non-trivial subgroups. So if you want a non-trivial subgroup with an additional property, since it doesn't have any non-trivial subgroups, it can't have any non-trivial subgroups with good properties. Okay. So the next thing is a definition, which is a little bit overdue. Let G be a group, H a subgroup, and G be any element of G. Then the G conjugate of H is the set of all things in the form G inverse HG. So what does that mean? Take anything little h and h, multiply on the left by G inverse, multiply on the right by G, and look at that set. And it turns out not only is this a set, but it's a subgroup. And not only is it a subgroup, it's an important subgroup. It's so important it gets a name. It's called a normal subgroup. And so another way of saying that this is a normal subgroup is if it has the property that G inverse HG equals H, we call it a normal subgroup. When you see G inverse HG equals H, how might you rewrite this? What's another way of looking at G inverse HG equals H? How could you rewrite this? So we've got all the G's on one side of the equality. How could you rewrite this? Yeah, so you get GH equals HG. How could you interpret that? So you could look at this as the left coset is the same as the right coset. This is not saying that when you multiply element by element, they're the same. It's just saying if I multiply H on the left by G, that set of elements is the same as the set of elements if I multiply H by G on the right. It's not saying that point-wise the multiplications are the same, but they are the same set that just may be reordered. Ideally, I would love to just say I have commutativity and I can multiply any way I want, but most groups are not commutative. So I don't have that property. This is a weakening. If G is commutative, will this be true? Of course. So every subgroup is normal if your group is commutative. But you could have a group that's not commutative and have a subgroup that has this nice property. Okay, any questions about this? I'm not sure why it's called normal. I mean, there's other ones, where when we get to solvable, they're called solvable because they used to help solve equations. Normal might just be related to, this is what we would normally hope happens. And this is what would be useful in terms of trying to understand things. Most subgroups, I mean, this would be a really interesting question. Take a bunch of subgroups and look and see what fraction of the subgroups are normal. Do you think it's a majority? And you could do this for a bunch of finite groups. I'm not sure if anybody's ever looked at that. If not, that would be a great thing to look at and just see what fraction of subgroups are normal. Okay, so the first thing is to show that G inverse HG is actually a subgroup. So how would you show that G inverse HG is a subgroup? What do we have to do? So remember, this is the set of all things G inverse HG, where little h is in big H. How would we show that this is a subgroup? What would we do? Okay, so the first is the identity. If we take H equals E, we get G inverse E G, which is just G inverse G, which is E, yes. So the identity is in it. What about associativity? Inherited. What's next? Closure. And so if we have G inverse H1G times G inverse H2G, what do you notice? They cancel. And so this just becomes G inverse H1, H2G. So we have closure. And the last is inverses. If I give you G inverse HG, I can just multiply by G inverse H inverse G. And that will be the identity. So it turns out that this is going to be a subgroup. So it's a subgroup that's very nicely related to what we're looking at. So actually, I just need a blank page. So I'm doing things in a slightly different order than the first section, just so I don't get too bored. So the classes you're supposed to have seen before taking this class. Linear algebra. And so you might have seen that if A is real symmetric, there exists an orthogonal matrix Q such that Q transpose lambda Q equals A, where lambda is the diagonal matrix, lambda 1 dot 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 lambda n. So with lambda, the matrix of eigenvalues. How many of you have seen this theorem? This is one of the big theorems in linear algebra. If I give you a real symmetric matrix, I can diagonalize it. Why is this useful? Well, if I want to look at a to the nth power, that's going to be the same as, Q transpose lambda Q times Q transpose lambda Q dot 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 Q transpose lambda Q. What do you notice about all of this? So what do we notice when we do this multiplication? Q transpose the identity. So this becomes the same as Q transpose lambda to the m Q. So if you think about what's going on, if I give you an n by n matrix, in general, it's a pain to calculate powers of the matrix. It's computationally intensive. But if I give you a diagonal matrix and I ask you to calculate a high power of the matrix, that's extremely trivial. I can calculate high powers of the matrix by just raising the elements of the diagonal to the nth power. So this is an example where rather than looking at an element, it's much better to look at a conjugate element. So this is, one of the reasons why we love stuff like this. Another is, going back a little bit further in your career, you might remember algebra 2, and if I give you an ellipse with A and B over here, the equation of the ellipse is x over A squared plus y over B squared equals 1. If I give you a ellipse that's rotated, the question is, what is the equation of the ellipse if it's rotated? Well, what you want to do, and this is one of the big ideas of linear algebra, is you want to choose a better basis. And so if I choose a new basis uv, where say uv is a rotation of xy, then in this new basis, I get u over a squared plus v over b squared equals 1. And I can write down the equation very nicely. It turns out that there's a matrix lurking in writing down the equation of the ellipse. I can really view what's going on as I take the vector xy written as a row vector. I take the matrix 1 over a squared, 0, 0, 1 over b squared, and then I take the vector xy, and that product is just equal to 1. This is the way of writing down the equation of a ellipse using the matrix. I can now substitute, and I can actually write down the equation of an ellipse in general when it's rotated in a matrix form. And I'll get a real symmetric matrix sandwiched with the vector xy equals 1, and that's going to be the equation of my ellipse. So in terms of why we're doing all of this stuff in abstract algebra, the who gives a damn, why are we spending time on this? Well, this is really something you should have seen in linear algebra or abstract algebra, but you might not have had the language to describe what you're doing. The big theme of linear algebra is to try to find what is the right perspective to look at a problem. What is the right viewpoint to do the computations? And so much of it is figuring out what's the right orientation. As a Bostonian, I hate New York City, but there's one part of New York City I have to tip my hat to as being well done. And that is, so who knows their New York City geography? Which part of New York City do I have to admire? Oh, yes. Just in terms of getting around, this borough is well constructed. Linear algebra is all about choosing the right basis, choosing the right coordinates. Which part of New York City has a really nice coordinate system built into it? I'm sorry? Not Brooklyn, Manhattan. You have a really nice grid structure. You have these north-south, you have these east-west streets. It's a really nice grid. You would be an idiot if you oriented your coordinate axis not to align with the streets. It's beautifully designed for something like that. In Boston, you can have streets crossing each other multiple times. It's interesting getting around. Linear algebra is all about finding which is the basis to look at things well. When you write down a matrix in linear algebra, as soon as you write down a matrix by putting entries, you've chosen bases. And depending on which basis you choose, the matrix looks different. The whole point about this theme in linear algebra is that if I choose the appropriate basis, my matrix is diagonal and it's easy to work with. And so if I give you an ellipse that's not aligned with the coordinate axes, rotate the coordinate axes. It's the wrong system to use to study it. And so all we're doing here is we're doing this conjugation idea. We're doing this G inverse HG. Why are we doing this? Note Q transpose Q equals the identity. So what is the inverse of the matrix Q? Q inverse is just Q transpose. So this conjugation that we're doing, that's really what you've seen in linear algebra with the Q transpose AQ. I assume they did it as Q transpose lambda Q, not Q inverse, when you did linear algebra. Oh, it's been so long. Normally they say Q transpose, not Q inverse, because the transpose operator is a really easy operator to do. Just flip the rows and columns. It turns out it's the same as the inverse for an orthogonal matrix. Okay, the next proposition is really nice. It gives us a way to find normal subgroups. So let phi be from G to G prime be a homomorphism of groups, then the kernel of phi is a normal subgroup of G. Now, it's possible that the kernel of phi might be all of G, or it might be the identity. In those cases, then unfortunately, we get a trivial normal subgroup. But if we have a situation where the kernel of phi is not the identity and it's not all of G, then all of a sudden, we have constructed a normal subgroup of G. And then we can use this to try to decompose G and break things down and understand them. So what I want to do now is I want to prove this proposition. We've already proven earlier that the kernel of phi is a normal subgroup. I want to reprove that just because it's been a while and this is the first class back. So let's just go through and do the calculations. So the first is proof that the kernel of phi is a subgroup. So what's the first thing we have to show? So what do we have to do if we want to show that it's a subgroup? Contains identity. So the first is the identity. Well, we know phi of E equals E prime, as phi is a group homomorphism. So E is in the kernel of phi. What's the next thing we have to show? Closure. So assume G and G tilde are in the kernel of phi. So phi of G equals phi of G tilde is the identity. Then what would phi of the product be? So we have a group homomorphism. Phi of a product is the product of the phis. So that's phi of G tilde, because it's a group homomorphism. And then that's going to be the identity times the identity, which is the identity. So we've shown that G tilde is in the kernel of phi. All right, so we've got the identity, we've got closure. What else do we need? Inverse. So if G is in the kernel of phi, then phi of G is the identity. But phi of G inverse is phi of E is the identity, and that's phi of G inverse. But what do we know about phi of G? It's the identity. Why is it the identity? Yeah, because we've assumed it's in the kernel. So it's in the identity by assumption. Therefore, phi of G inverse is equal to the identity. So G inverse is in the kernel of phi. And what's the last one? How do we prove associativity? Inherited. Without risk, or without too much risk, you can just say it's inherited. That almost always works. Yeah, it's inherited. It's important to remember, where do things live? Where do the elements of the kernel of phi live? They live in G. So if they live in G and G is associative, and you live in G, then you're associative. And so it will be inherited. So this is the proof that it's a subgroup. All right. Now we want to prove that it's a normal subgroup. And so I'll just do a little bit more space. So now, proof that, given phi from G to G prime, kernel of phi is normal. So we must show G inverse kernel of phi G equals the kernel of phi. Right? That's what it means to be normal. Okay. So I claim it's enough to just do one direction. We're just going to do this direction. So we're going to prove that G inverse kernel of phi G is contained in. So we'll prove G inverse kernel of phi G is contained in the kernel of phi. Why is that enough? If we do this, show for all G and G, then take G inverse, take G to be G inverse. Then we would get G inverse kernel of phi G inverse is contained in the kernel of phi. But what's G inverse G? I'm sorry, what's G inverse inverse? G. So this would be G kernel of phi G inverse is contained in the kernel of phi. And then what can I do to both sides now? So I've got G kernel of phi G inverse is contained in the kernel of phi. I can move the G's to the other side. And so this becomes the same as the kernel of phi is contained in G inverse kernel of phi G. This is why it's enough to just do one direction of the inclusion. If I can show for any G that G inverse kernel of phi G is contained in kernel of phi, well, I technically need to prove that the kernel of phi is contained on the left. Well, since G was arbitrary, just take G to be G inverse. And then when you go through, you then get, you do the same calculation, you would then get G kernel phi, G inverse is contained in the kernel phi. Oh, that's the same thing as the kernel phi is contained in G inverse kernel phi G. So it's worth spending some time and just, really looking at this. It tells us that it's enough to do just one inclusion. Again, you've seen something similar to this in linear algebra. If you want to prove that a subset is a vector subspace, what you do is you show if I take any two elements, any two scalars A and B, and any two vectors V and W, AV plus BW is contained in the set. If I can do this, then I have a vector subspace. And this becomes a really nice condition to check. It's always a question of what is the minimal amount of work I need to do to prove something. And instead of trying to prove both directions, this is telling me if I just prove one direction, that's enough, because the other direction I get from a trivial calculation. Okay, so now that I have this, now the question is, can I show that G inverse kernel phi G is contained in that? So now, proof of this. So let H be something in the kernel of phi. Consider G inverse H G. Where do we have to show G inverse HG lives? So where do we want to show it lives? In the kernel. So what should we do to it? Yeah, take phi of it. I mean, basically, there's nothing else we can do. We're trying to show it's in the kernel of phi. Let's apply phi to it. So phi of G inverse HG is phi of G inverse, phi of H, phi of G, because phi is a group homomorphism. But what is phi of H? It's the identity, because this lives in the kernel. So this is just phi of G inverse, phi of G, which is phi of G inverse G, which is phi of E, which is E prime. So G inverse HG is in the kernel of phi for all H in the kernel of phi. And that finishes the proof. So this is a nice proof. It shows that we have a way of constructing normal subgroups. We don't know if these normal subgroups are non-trivial, but at least we have now a possible avenue to constructing them. Okay, so the next proposition is just isolating some of the stuff we've already said. If you look at part C, you will notice that there is a vertical line between the and map. Does anybody know why there's a vertical line between the and map? Because I did not realize my cursor was between the and map when I took a screenshot, and so that is the cursor. Fortunately, I can just start writing in white, and there we go. And now it is fixed. Okay, so proposition 610. G is a group, H is a subgroup. If G inverse HG is contained in H for all G and G, then H is a normal subgroup of G, I is enough to check one inclusion. We just did that. This is just isolating this into a proposition so that if you're ever doing an exam or a homework problem, you can say by 610A, it's enough to just do one direction. B, if G is in G, the conjugate set G inverse HG is a subgroup of G. We actually did that earlier. This is basically just isolating out a lot of the stuff we did. Why do we care about B? We saw applications from linear algebra. When we were looking at high powers of a matrix, it's very painful to calculate high powers of a matrix. But by diagonalizing a matrix, and because Q transpose is Q inverse, this allows us to do calculations very quickly. So then the next one is for all G and G, the map H goes to G inverse HG, defined by taking some element little h and h, sending it to G inverse HG, is a group isomorphism. So if big H is finite, then all of its conjugates have the same number of elements. All right, so if you think about what's going on here, we're basically just saying that we have a homomorphism between two groups. If you think about it, we showed G inverse HG is a group. We're just saying that the group size doesn't collapse. What would it mean if, say, G inverse H1G equals G inverse H2G? You think you could have two different things going to the same thing? Do you think this is possible? Well, wait, we have to prove that it's a group isomorphism, right? And so, do you think G inverse H1G could equal G inverse H2G? Yeah. That would imply H1 equals H2 by canceling. We have a group. We can multiply on the left by G, we can multiply on the right by G inverse. So this is how you'd prove injectivity. And then surjectivity. How would you do surjectivity? So given some element in G inverse HG, what is mapped to it? So a lot of times the proofs come down to essentially proof by definition. I remember my freshman year being very frustrated when we finally figured out that the answer to one of the problems was by definition. And it was just unwinding what the definition was. What does it mean to be an element in G inverse big HG? So if X is in G inverse HG, then what must be true? So G inverse big HG is the collection of what elements? Yeah, then there exists a small h in big H such that X is equal to G inverse HG. Can you give me an idea of what we should apply this map to? The map that sends elements in H to conjugating by G, so G inverse on the left, G on the right. So if we define, C of Y to be G inverse YG, then what should I take for Y to get this element X? Yeah, just take which element? Yeah, just H. Then take Y equals H, and you get, C of H is G inverse HG. Surjectivity is not that hard. If you want to give me some element in G inverse capital HG, I've got to be able to write it of the form G inverse little hg. And then just that little h, that's what you map. That's what you send to. Okay. So the next one is basically saying that if you have a normal subgroup, then everything is well defined in terms of coset multiplication. So let G be a group, let H be a normal subgroup. So a lot of times people use different letters for normal than H. Any thought about what you might use for normal? N, right? N would be a really good choice. And you might say, let's mutually agree that we shall never use N when talking about a subgroup unless the subgroup is normal. So you might have a subgroup and you might not initially know that it's normal, so I can't use the letter G. I'm sorry, I can't use the letter N, I might use the letter H. And we've agreed we're never going to use H unless we know that the set is a subgroup. And if we don't know it's a subgroup, what letter might we use for the set? S, right? And this just helps you to quickly glance down and see what's going on. One of my thesis students had the best start to a thesis defense at Williams, where he had an equation that filled an entire page, and then he expanded the left-hand side and the right-hand side, and it was either 10 or 20 pages each to expand the left-hand side and the right-hand side. And his thesis was to show that they were the same. And so you want notation where you can quickly glance down and see what's going on. And you want to just be able to do almost automatic. Oh, okay, H is a subgroup. And it's a normal subgroup. So what this is basically saying is that multiplication is well defined if H is normal. We've basically done this. So, see the book for the rest of the details. But that's basically what we've been doing today. Was everything we've done from the very beginning says if we have this normal condition, then the coset multiplication is going to work out. A question you could ask is there anything weaker than normal? So make me feel good. Everybody remembers the diagonalization theorem for matrices. Your real symmetric matrix can be diagonalized. A complex Hermitian matrix can be diagonalized. You can ask, what is the most general matrix that can be diagonalized? I think frequently you do normal matrices. Did you do normal matrices in linear algebra? You commute with your complex conjugate transpose? Pretty sure. Okay, never mind then. All right. All right. So the next one is a lot of gobbledygook. And I will recast the last in language that makes much more sense than something that you've seen before. So G is a group, H is a normal subgroup. I'd like to write N, but we'll do H. The collection of cosets G mod H is a group by the well-defined group operation. So this is what we've basically been doing. That you give me two objects, I multiply them, and it doesn't matter which coset representatives I use. If you had to worry about which coset representatives you use, then we can't make any progress. The second one is that the map G going to G mod H, which sends phi of G to G times big H, is a homomorphism whose kernel is H. So G mod H is going to be a group whenever H is normal. So if it's a group, what does it have to have? So every group has to have what? An identity. What would be the identity of the cosets of G by H? So G mod H is a group as H is normal. What is the identity? So what would be the identity? So it's going to be some coset. Which coset is going to be the identity coset? All right, let's take a step back. If you have a group homomorphism, do you know anything that gets sent to the identity? The identity. So if you take a step back, you know a group homomorphism sends the identity to the identity. We have a map that sends G to the cosets G mod H. The identity goes to the identity. So what must the identity coset be? Just H, or I want to write H as something times H. Identity times H. That should be the identity coset. And what part B is saying is that if I look at this map, the only thing that gets sent to the identity coset are the things that are in H. That makes sense. Anything else that's not entirely in H is going to be sent to a different coset. So again, I urge you to go through and put in the details of all of this. Part C is we now start having some map from G to G prime. It's going to be a group homomorphism with the property that H is contained in the kernel. Then there's a unique homomorphism lambda that takes the set of cosets and maps it to G prime. And then in part D, if we take H to be the kernel, and then we look at this homomorphism, we get an isomorphism between G modding out by the kernel and the image. So rather than proving this, I want to just convert this to normal English that you've seen before. All right, let's look at simple maps. Here's one of my favorite maps. F of x is x squared. If you were to plot this, what would this look like? It would be a parabola. So we have F is a map from R to R. Is this a bijection? No. So it's not a bijection. So why is it not a bijection? Good, so it's not injective. And why? Any other reasons why it's not a bijection? I'm sorry? Yeah, and it's not surjective. So it really, really is not a bijection. It's not injective, it's not surjective. But we can modify this. And instead of considering F to be on all of the reals, let's just define it on the non-negatives. And instead of looking at the output as all the reals, let's look at the output as all the non-negatives. Is it a bijection now? Yes or no? So now I look at the square map from 0 infinity to 0 infinity. Is this a bijection? Yeah, yes. It's now going to be injective. You're not going to have two things sent to the same, and everything is hit. So the lesson we should have learned here is that if you take a function that may not initially be a bijection, you might be able to make it a bijection with some trivial modifications. What's one modification? Well, it may not be surjective because it doesn't hit everything. Okay, let's just get rid of, from our conversation, the things it doesn't hit. So instead of considering it as a function to all of R, let's consider it to a function of the image of F. If you look at the map from F, from some set to the image of F, is it going to be surjective? Yes, because you're looking at the output as the image of F. These are all the things that F hits. It's clearly going to be surjective because you've restricted yourself now to just the things that F hits. That's what this is doing over here in the last statement. That's why we're getting an isomorphism. Rather than looking at it as being mapped into all of G prime, don't look at it as mapping into all of G prime. Look at it as just mapping into the image. Okay. The next thing we're doing is we're modding out by the kernel. And that's taking into account the fact that it may not be injective. So this is the general principle, is that if I have something that is not a bijection, I can often make it a bijection by doing some trivial modifications of my target space and my outcome space. You know, my input space, my output space. Okay. And then For the next class, what we're going to do is we're going to start talking about groups acting on sets. And so there's a lot of beautiful theorems that give you information about what does a group look like as you know its order. The smaller the order of the group, the easier it is to analyze. As the size of the group grows, it becomes harder and harder to figure out precisely what is it. And the whole point is we're going to try to develop and use some of the concepts that we've been learning to understand what groups look like if they have certain orders. And there is a tremendous amount you can do. This is a first class. We will only scratch the surface, but we will completely analyze some things. One of these we'll prove is every group of order p squared is abelian. So there are no non-abelian groups of order p squared. Well, what about p? It starts getting more complicated the more options you have. All right, so this is a good place to stop for today.